Hello. Today we will be talking about support vector machines, which are very popular among the classifier algorithms. And in this, we would be talking about decision boundaries with large margins, sometimes also called the widest street approach. So we now get a feel of what actually SVMs aim to do. Consider the set of data points where these blue dots, thick dots, belong to the positive class and these crosses belong to the negative class. And we would wish to find a decision boundary or a separating hyperplane, in this case a line because it's a 2D data. So we have drawn three lines. We will look at each of them one by one. This black dashed line, it is separating the two classes. No issue in that, we can see it clearly. However, look at this blue point, which is so very close to the line. However, all the crosses are quite far away. So this black line somehow doesn't look like a good separating line. Now look at the red one, the red dashed line. All the blue dots are very far or quite far away. However, we again see a cross belonging to the negative class, which is very close to the line. So this again might not be very suitable. Now we see this thick green line and we note that both the positive class and the negative classes, that is the cross, is so far away and even the dot is fairly far away. So this green line would be a natural choice for all of us as the separating boundary. However, we have not gone through any mathematics, even just by visual inspection, we choose this line. Okay, so maybe mentally we are thinking about a margin around the line separating the two kinds of data points. Now let us have a recap of actually the concept of classification, how actually we look at the classifying function. So in logistic regression, the probability P of a class belonging to the positive data belonging to the positive class, given the x value and the parameters w, we model it using a sigmoid function, which is the logistic, also known as the logistic function. So we have this gz, we would all recall, is 1 divided by 1 plus e to the power negative z. So we predict the 1 on an input x if this hx value, hwx value is greater than 0.5 or the wtx is greater than 0. For a positive example, the larger wtx is, the greater is hwx and the greater the probability, and our confidence of prediction also becomes higher. See, our logistic function is like this, and this is the 0.5 mark. So, and this is our WTX on the x-axis and our GZ on this, GWTX on this side. So, even though we would be predicting y equal to 1 for HWX greater than 0.5, we would be more happy if our HWX was closer to 1, which would occur when WTX is much, much greater than 0. This is our 0. Similarly, we would do the same or have the same logic for the negative class. The negative class WTX less than 0, we say the HWX falls below 0.5. So we say the class belongs to the y equal to 0 class, the data point. However, we would be more confident if this value was closer on the away from the 0 point, or WTX is much, much less than 0. So, we are modeling classification of a data point using the sigmoid function in the logistic regression algorithm, and we say that 0.5 is our deciding threshold for declaring as y equal to 1 or y equal to 0, but still we would like it if the values were much higher. So, in short, for a training set, we claim to have a good fit if WTX is much, much greater than 0 for the positive class, and I'm sorry, this should be less than, much, much less than 0 whenever we have the negative class. We again have an example. We come back to the example, and we have taken 3 data points. As we can see, this separating line is clearly demarcating the positive and negatives, but the C is very close to it. B is fairly far away and A is very far away. So, our prediction regarding the data point A would be very confident as a positive sample. For C, we might be slightly shaky because it is too close, and any change in the boundary would push it to the other class, negative class. And point B, however, we can claim is quite safe. So, we can see here that around the decision boundary, after up to a certain distance, we feel safe in predicting a class, and within that, we will not be so sure. So, this is what SVMs aim to find: a large margin, also known as the widest street approach. So, the basic idea is about separating the data with the large gap or margin. So, this is my decision boundary. This is the decision boundary, and these are our, on both sides, we have the margin. So, this is the aim of the SVM classifier algorithm, that we find a hyperplane or a decision boundary with a margin on both sides separating the two types of examples, so that our confidence of predictions is high. And how this is done, we shall very shortly see. Thank you. Thanks for watching.